Okay, I think we should get started for the afternoon sessions. So it's my pleasure to introduce Bill Dorland, who's going to lead 4 sessions, tutorials, and lectures on computing on GPUs, a new sort of newly developing field, rapidly developing field. He's going to provide us with some insights and some hands-on experience on using GPU clusters for scientific computing. So Bill is no stranger to Princeton. He got his PhD here in 1993, working at the Princeton Plasma Physics Lab on magnetic confinement fusion. Bill is best known for his work with AstroGK, which is a numerical technique that he developed or helped co-develop for simulating nearly collisionless plasmas, and in particular looking at anomalous transport in tokamaks, a very serious issue which limits the efficiency of magnetic confinement fusion. And he's made some fundamental contributions into our understanding of plasma dynamics through simulations using the AstroGK code. And I think what's particularly interesting to this audience is he's also interested in astrophysical plasmas, and in particular the role of nearly collisionless plasma dynamics in interpreting observations and dynamics in a number of systems. For example, very low luminosity accretion onto compact objects, and dissipation of turbulence, MHD turbulence in astrophysical plasmas. So he bridges both the plasma and the astro communities and brings his expertise to both. So it's our great pleasure to have Bill giving us these lectures.
Thank you. So we tend to think of the code, instead of AstroGK, we call it AstroGeek, because that just sounds better. Okay, so I'm not going to talk to you today about what I do to get paid, which is physics, astro. Instead, we're going to talk about how to compute on new technology. And I think, yeah, so there's a lot of people that work together at the University of Maryland, primarily in computer science, who've been working on this. And my slides will be available to you, and I've posted a lot of the material that I'm going to show and talk about over the next few days on the wiki. And it changed last night around midnight, so you might, a few days ago, you'll see new stuff there now. In particular, Frank Herman is here. I don't know if he's in the room right now. Yep, he's in the back. And so he and I will both be available to answer some questions and do some of the hands-on discussions. And Ramani Duraswamy and Nail Gumarov really are the experts at Maryland in doing this kind of computing. So it may be the case that over the next few days, if some of you have some particularly challenging or interesting questions, we may bring them into the discussion as well. Okay, so I think this is important. You know, whether you're interested in smooth particle, hydro, MHD, symplectic integrators, rigid bodies, PIC, numerical relativity, whatever it is, a few of you from each of those fields are going to find a topic on parallel computing interesting. So I will not be offended in the least if most of you get up and leave. It won't bother me. I've given you this slide so that you have an indication that that's okay. You come into contact with computing in lots of different ways when you're a grad student or a postdoc. Oftentimes, as was stated by Mike Norman yesterday, you come in and you think, I'm going to write a code, discover something, write papers, get tenure, everything will be fine. Other times it's even worse. You're given a code and told, run the code, write papers, get tenure, everything will be fine. And by the time you get the code, it doesn't even run on the computers that are out there anymore. So the transition that's going on right now is a fundamental one that will affect everybody here that stays involved in computing. I can guarantee you that. Where we are is, it's best to take you back a few years. When I was a grad student, 1988, there were vector supercomputers all over the place. And a vector supercomputer, in those days, the goal was to get to a gigaflop of computing power, which you can now get pretty easily in a lot of places. The goal was to get to a gigaflop of computing, and in order to use the vector supercomputers effectively, you had to write your code in a certain way. And it wasn't hard to learn. It was a sort of syntactical monkey see, monkey do 80% of the time, and 20% of the time you had to actually think and understand what was going on with all the memory registers and all that kind of stuff. But it was really quite easy technology to have a a simulation idea, to write code that would run effectively on those machines, and then to execute it. From 1980 to somewhere around 92, 93, there was a huge transition when commodity processors got so cheap and networks got so cheap and the vector processors of the time were getting so expensive that it became impossible to buy a vector computer that would be as efficient as a whole bunch of PCs wired together with an Ethernet connection. And it was a time of great tumult. When I was a grad student here, several people in computer science left. They made their money by selling plans of what a parallel computer could look like. I mean, that was sort of what you did in grad school. And then a little later, everybody started leaving to go to Wall Street, but that was different. In the beginning, it was parallel computers. And anything you had an idea about for how to make a parallel architecture out of commodity parts was golden, and somebody would pay you to think about it and develop that. Well, what flourished in that time was tons and tons of companies, many, many different architectures, many different programming styles, and many different concepts which were different in detail. Some would have a different relation to memory, some would have just lots of different things. And it was very, very complicated because you could not see what was going to win. And so you might invest a month or a year or 2 years learning what seemed like a sure thing. Thinking machines had really big posters and really nice looking computers, and the connection machine looked like it was going to last forever, and then you turn around and they're gone. And you've just spent a year learning connection machine Fortran or whatever it was called, CM Fortran. So in those times, it was clear that vector supercomputers were going to go away because nobody was willing to pay for them in the onslaught of all these other kinds of parallel computers. So it was clear that you had to change, but it was not clear what you should do next because there were too many different choices. Now we're at the second version of that. It's extremely clear at this point, and I'm going to go over it in my talk with you, that the computing model that all of you have seen or used or sort of implicitly assumed is under the hood in your computer is going away. And that's the basic, what is called a latency processor or a CPU. And the basic idea behind those is you write code that is reasonably optimized. You know, you've all probably looked at single loop optimizations and various kinds of unrolling and things you can do to take advantage of little gizmos and so forth that are offered on a given chip, or you've used a compiler that has chip-specific enhancements that will make your code go faster on a particular, if you compile it on the right machine. Intel currently has really great stuff in the Intel compilers for that. But you don't have to think too hard. Well, that's changing. Instead of having one processor that is exquisitely sophisticated and extremely complicated, and which has compilers that have 10 or 15 years of work put into them to develop branching code. For example, right now, in a lot of the code that you write, most of the code is being executed multiple times, and then the answers are thrown away because there's all sorts of conditional execution that goes on. There's lots and lots of data that's pulled out of memory without you ever explicitly asking for it. It's all brought in, and the part that's needed is used, and everything else is thrown away. And all this stuff is done behind your back without any special work on your part. And it's great because it runs fast, but it's just like the parallel supercomputer, the vector supercomputers of the 1980s. The model has run out of steam, and it's because there's a cheaper, faster way to do all that. And unfortunately, the bad news is you're in the position of not knowing what the right way to get out of this is, just like people were not in the right position 20 years ago to know what was going to be the winning or the losing technology. It's much more important not to be the loser than it is to be the winner. And yet it's clear that you need to get involved in what's going on. So, 10-minute prologue, by which I mean I know that most of you are, no one came to this meeting to learn parallel computing, and I'm not going to be able to teach you parallel computing if you don't already know it in a couple of hours, but I am going to go over with you what the change in the chips is and how things look, and then we will go in the next 3 sessions with whatever subset of you is left and talk about how you can implement basic code ideas to take advantage of the kinds of changes that are going on. I should say one more thing before we start. We started out at Maryland looking at several different technologies. The basic idea that I'm going to talk about with you is very easy to understand. the most common commercial product that computers are used for today is video games. There's, if you talk about disposable income of families, what are they going to spend it on next? Lots and lots of people get their Wii or their Xbox or the PS2 or PS3 or whatever it is by now. And there are millions and millions and millions of video cards that have been optimized to make video games as thrilling as possible for adolescents, right? These things are much faster than any CPU you have on your computers by a large factor. And I'll go over that with you. It's currently about a factor of 30, and it's going up to a factor of 30,000 in a couple of years. It's just crazy difference, the speed you can get out of a video processor compared to a CPU. And so I want to talk to you about that. And you have to take advantage of it if you're going to do a computation that requires power to assert, to find a new idea. If you've got an idea that doesn't need a real powerful computer, no big deal. But if you're going to integrate something, it's going to need this kind of technology to keep up with everybody else. Okay, so this is pretty neat. Oh, it's too bad. The right side is cut off. It's not cut off here. We'll deal with it. Okay, so Moore's Law you've all heard. Aha, look, magic. Thank you, magic person. See what video cards do for you? It's just great. Just say, fix it. Okay, this is actually the original plot from Moore's paper that showed Moore's Law. So he put a couple of points, 5 points on a log plot, and declared a law. And originally, see, it was easy back then. He probably could have gotten tenure for that. So originally, it was going to be a doubling of the number of transistors on an IC every year. And later it became clear that that was more like 18 months. And it's been remarkably good for a very long time, right? Now I get this slide from Bill Dowley's slides, which I've posted for you on the web. I'm not stealing them from him. He's the chief scientist at one of the companies that makes these video cards. He was just at my campus for a day talking to us, and I think I found some of his slides particularly useful, so that's why I'm using them. I want to make sure you see anything down here is from Bill Dowley. He was the chairman of the computer science department at Stanford for many years and just switched to go back into the commercial world to work on this project. So he's somebody with a lot of credibility. Okay, so Moore's Law did not predict, in this paper, he did not predict that the processor performance would behave in any certain way. He did predict that there would be an unfavorable power scaling at constant functionality, and advances in architecture were going to turn, the idea was that advances in architecture, how to use all these transistors that were going onto the chip, would turn into a performance scaling. So before I go on, I want to remind you the wiki resources in this part of the meeting are more important than they are in the other parts, in part because it's impossible to communicate something as detailed as the syntax of a program that none of you actually care about, these sample programs, effectively because at many different levels. So what have I done? There's something called CUDA-U, or CUDA University, which is a very large website that has tons and tons of examples, lectures, notes. It's compiled lectures that people have taught this material over whole semesters at different universities at Illinois, Maryland. So it's a lot of terrific, learn it on your own, sink or swim kind of material. There's also notes from a course that my colleague gave at the University of Maryland last semester. There's a talk from John Turner. I have no idea who John Turner is. He may be here. Are you here? No. But I found his talk on the web a few years ago, and it's an extremely insightful view of what was going on. This is from 2 years ago, and it's just an outstanding view of what was going to happen in the CPU, GPU kind of world, and it's proven to be correct. We're 2 years out since, so I urge you to look at that talk. It's really good. Be aware, though, it's a large PDF, so it takes a while to download. Then I have Bill Dowley's talk, which I've cribbed about 5 or 10 slides from, and then there's other stuff. So I want you to know about that. So back to Moore's Law. Moore's Law says it's going to require advances in architecture to turn the device scaling into performance. Well, how does that work? Moore's Law gives you more transistors, And somebody out there determines how to put all those transistors together to make a computer or a computer chip. Those are the integrated circuit architects. And then people like you and me turn this performance into actual codes that we can figure out useful things like about the universe. Okay, so this is a really important slide. It's from a paper by Bill Dally in 2001. And the basic point here is that we're here somewhere in the mid-2000s. I guess we're way over here now. In 2001, when this paper was made, there was a 30-to-1 discrepancy between this blue curve and the green curve, and I'll tell you what they are in a second. The blue curve is the actual performance in picoseconds per instruction on chips of the day. And the green curve is what you would get if the architects could take advantage of all of those transistors in the way that they had done in the past. Okay? So in other words, if you just look at the raw speed of computations available on a chip, that was increasing year on year at 74%, but the microprocessor performance improvements were only at 50% a year for several years, only. Okay? Well, somewhere around 2000 that changed, and we've dropped over to 19 or 20% a year, which still seems great. You still don't ever want to buy a computer because it'll be better next year and cheaper, but 20% a year is now far off the curve because we're not able to use the model of the dominant chips that are out there, the Pentiums and so forth, with a large processor and lots of antecedent stuff around it to bring the data in and do conditional compilation and execution. So we're way off the curve of what the hardware can do, what you can really do with the silicon. And so right now it's in the neighborhood of 30 to 50 to 100 to 1. And extrapolating out in just a few years, right, well within your academic time, the ratio is going to be much, much larger. Who knows? 10 to the 4. So if you ignore, this is the genesis of the comment that I made at the beginning, if you ignore the change in the technology that is associated with the architecture on the chip, you're throwing away a factor of about 30,000 relative to the other people in the room who take advantage of it. And it's hard to do cutting-edge science if you give up a factor of 30,000. So this is a plot, again, which shows, in particular, looking at single-thread processors, that's the kind we all have come to know and love, performance versus calendar year, and the 52% curve is on here. And around the early 2000s, it rolled over and turned into the 20% a year number. So there's reasons for this. But let me go ahead and introduce to you show you the flip side, which is how GPUs have done, graphics processors. So if you put Moore's law in terms of gigaflops per device, we'll call it either a CPU or a GPU, and I don't want to call it a processor yet because there's some nesting of processors that goes on. If you look at the gigaflops versus time, this is Moore's law. This is the thing that it's a little bit less, it's 20% instead of 50% increase year on year, so it's not quite as large as Moore's law like I just showed you, right? But this is the improvement that you're all used to getting, and on this curve it looks positively dull next to the performance improvements that are coming about on graphics processors. And it's very simple what's going on. Instead of having one processor, they've stopped putting one processor per chip and are putting more and more processors. And so after this curve, somewhere over here, we're at 256 or 300 processors on a single chip. And that just, if you can take advantage of all those processors, you get enormous speed-ups in the performance. Now, let me just say, there was, by way of education, there was a period of time when this gap opened up. If you search on Google with GPU, General Purpose Graphics Processor, whatever U is, unit, then you'll find that there was a community of people in here who said, who were basically following in the footsteps of the gravity pipe and other things like that, that said, hey, there's some specialized computing hardware out there, and if I write my code in the specialized way that the hardware can use optimally, then I'm going to get a big benefit over everyone. The trouble was the GPU only spoke graphics. So you had to recast your problem in terms of a graphics problem it's not too bad. Graphics problems are two-dimensional arrays, and you're doing lots of things with them. There's all these chips have on them interpolations, rotations, dilations, all the kinds of things that you would like to do, sums, differences, max, min, all kinds of things that you'd like to do to your large arrays of data in science are there, but you had to pretend it was a picture and manipulate it that way. So this was I was not involved at this point. This was a real serious computer science type thing. And somewhere back here in 2006, DARPA, the Defense Advanced Advanced Research Projects Agency, did something good. They went to all the makers of all the graphics chips in the country, and they had observed that this gap was opening up, and they said, we will fund you to make the graphics cycles available to scientific programmers. Just give us standard calls like an FFT and a matrix multiply and multiply by A times B plus C, all those kinds of things. Just give us these standard instructions for your graphics processor so that we don't have to have all of our people pretending they're doing graphics. And that happened, and it's been an explosion. Suddenly you have NVidia, which is one of the competitors, and it's the one that I've settled on to. You have IBM, which makes the Cell processor, which is the PlayStation 3. The Cell BE is the Cell Broadband Engine. That's the basis of a computer at Los Alamos called Roadrunner. Has anybody here heard of Roadrunner? I just want to see. Okay. Gives me an idea who I'm talking to. Right. So the Roadrunner computer is a petaflop computer that's all built, it's got CPUs and Cell broadband engines, which are basically PlayStation 3 video cards, juiced up a little bit. And AMD bought ATI, and so that's all now one company. So all of these things are possible, and there's lots of different programming paradigms. And the problem you face, as I said, is it's not clear who's going to win. Okay, but you all want faster simulations. And it's important, when you look at parallel computing, oftentimes you can be fooled into thinking that a weak scaling is all you need. What is the difference in weak scaling and strong scaling? Weak scaling says if I've got a problem I want to do and I double the problem size and I double the number of processors, I can complete it in the same amount of time. That's fine. If someone gives you 100,000 processors, there's few of us that have a problem in mind that really needs to be 100,000 times bigger. We'd instead got lots of problems we'd like to do that we'd like them to be some combination of bigger and faster, right? So weak scaling is doing the larger problems at the same speed, and strong scaling says if I take the same problem and I put it on different number of processors, does it speed up proportionally to the number of processors when I look at the wall, right? So I calculate plasma turbulence, as Jim said, and we do most of our calculations currently at national supercomputing facilities on hundreds or thousands, or these days 100,000 processors. And this is the kind of thing that my students and postdocs have produced at various times. This is the AstroGeek code. This is a strong scaling. So we found a problem that would fit on one processor of a particular IBM SP that was really slow. It's old now. I think it's been decommissioned. But they had lots of memory on a single processor. So we could fit a problem onto one processor and run it, and then we could do the same problem with no changes, just changing the number of processors, all the way out to 2,000 processors. And what we found is out to 1,000, we could get 1,000 times speed up, right? So that's great, because now I can do I can choose another problem which fits on 100 processors, and that will speed up, significantly further. So strong scaling is terrific, and then this figure shows you that we got the same strong scaling. This is the same problem now on different computers, so it didn't always fit on one processor if they had less memory. But the same problem on lots of computers, in each case ran was linearly sped up over a large range in problem size. I'm not going to teach you how to do that, but this is something that everybody wants, right? So what does GPU offer? This is the only sort of selling part that I'm going to do. We took the same code that was doing these calculations and ported it to a GPU in a single day, and the performance that we got was only on one GPU. I did not, in that one day, port it to multiple GPUs, okay? So I can only do 1 point somewhere over here on one, And then if the scaling holds, this is what we will get. And it's just great. Huge speed ups. So we've already achieved this point. And if we can get multiple GPUs talking together, we will have achieved an enormous speed up in performance over what we were getting at national supercomputers. And the difference is a computer like this one is $10 or $20 million, and this is a desktop. So it's great. Okay? Maybe not a desktop when you get into multiple, but right here, that's a desktop computer. So it's performing as well as all this. Now, does anyone see the major problem that's sort of obvious here? Yeah, good. I had no idea how sophisticated the crowd would be. The critical problem is exactly memory. GPUs are screamingly fast, but they only have a few gigabytes of memory. So we're accustomed to doing a certain size problem and doing it fast. And if we're stuck with only being able to do 1 or 2 or 3 gigabytes, there's not many of us here who have problems that we need to do fast that aren't of a particular size. You know, we don't necessarily need to do much, much, much larger, but they can't be too small. So that's the challenges. And I want to show you some cool stuff from this guy. Okay. So this is from the talk that he gave at Maryland a couple of weeks ago. And he shows us now we're talking about NVIDIA, okay? So this is the NVIDIA chips. So this is a silicon wafer, 20 millimeters, 2 centimeters on a side. And he went over what you can put on such a chip. You can put 4,000 64-bit floating point units on the chip. And so they have a tenth of a square millimeter. That's the whole thing you need to do a floating point operation. And it takes 50 picojoules per operation, and you can drive it at 1.5 gigahertz. You can fit 4,000 of those on a single chip. Now, that would mean you have no memory, no communication, et cetera. So you can't actually make a computer right now with 4,000 processors per chip, although you could print the chips, if you see what I mean, right? Additionally, and that would run at, this would run, if you could run all of these at once, this would run at 1.4 tera operations, 1.4 trillion operations per second, and consume about 70 watts. Now, if you're dealing with integers, there's a 16-bit memory accelerator, anyway, to do the integer arithmetic to find out where all your data is and so forth. These are truly tiny. These are fixed point processors, 0.002 square millimeters, 50 times less energy, 50 picojoules per operation, 1 picojoule per operation. You could fit 200,000 of those on a chip with today's technology. If you ran this one, if you could do all your computations with that would run at 70 tera-ops. The problem is how you move the information around on the chip. Communication is extremely expensive when you can put that many processors together. So just focusing here for a second, if I've got a floating point unit here, and I want to move data, and I've got a memory element over here that's 10 millimeters away, it takes 250 picojoules in 4 clock cycles to move a word of data from here to here. So the problem isn't doing the computation anymore. It's even moving the memory around on the chip. And the rest, and then talking off the chip is a different cost. Okay, so those were the slides from him. Back to this. And then, so what NVIDIA's done is put all that together into, this is a picture of one of their silicon chips. This is their advertising, ultimate throughput computer. I do find them to work pretty well. So this is something you could buy a couple of months ago, the Tesla T10. There's 240 scalar processors. It runs at more than a teraflop on a single chip, and that's a trillion floating point operations per second. This is a slide from NVIDIA, right? It says, as if it's a great thing, exposed hierarchical memory. The rest of the talk is really about that. And 10 to 200 times performance improvement and compared to, say, a Pentium or a what are they called with the X? I always want to say Xenon, but that's not right. Xeon, thank you. Okay, so these guys really do work extremely well. They've been built, and whether we as scientists ever use them at all, they're still going to print out millions of these and sell them to people playing video games. So it's not the case. That's the reason that you have to get on the boat. It's not because this company is going to sell lots of these to everybody in science. It's because they're going to be essentially free for science based on the other market that they have. Okay, so the key to performance is memory management. And there are many, many levels of memory. And it was described in the previous slide from NVIDIA as exposed and hierarchical. What that means is instead of you being able to depend on the compiler to recognize caching opportunities, to recognize loop on rolls, to recognize all the different kinds of things that you read about in the manual for how to make your code go faster, all of that's done for us with modern compilers today. That does not happen for you yet in this new world. So there's many different levels of memory. Anything that's off chip, that's on the CPU that acts as the host of the GPU, or for heaven's sake, you hope not, that's on another GPU, which might as well be on Jupiter in terms of computing time, that's off chip. That's one level of memory. On chip, there's 4 different kinds of memory. There's global memory that everybody has read-write access to, and which can or cannot be synchronized depending on how you decide to write your code. There's texture memory, which is a stupendously beautiful thing for, I predict it'll be very powerful for SPH and PIC types of operations, because in texture memory, you can, in one clock cycle, let's say you've got a potential versus on a 2D array, and you need to interpolate a value of the potential somewhere off array. Normally, you have to read 4 bits of the 4 points and then do the whatever kind of interpolation, or if you're going to do splines, you have to read more points. You have to do all that to get your one piece of information, and that takes many clock cycles. Because a graphics processor needs to interpolate all the time to get pixels and everything right, they built in all the interpolation stuff. So in one clock cycle, you can pull off whatever you need from gridded array. It's really great. That's texture memory. Constant memory is different than texture. You don't get automatic interpolation off, but constant memory is data which nobody's going to write to during the process of whatever little loop we're doing, but everybody might need access to. And when I say everybody, it means all the threads or all the parallel processors that are accessing this piece of data. So constant data, all right, I just killed this, no. Constant data is read-only, very fast access. Shared isn't necessarily shared by everyone. Shared means groups of us can share information and easily block reads and writes to synchronize our operations. So we'll go back over all this with people, with the subset of you that really wants to know, but what I want you to see is that there's many levels of memory, and I predict that the superstar programmers that write great code in 5 years are going to be people not who know about algorithmic complexity, but more about memory management and memory complexity. That's where the future is. And so if you're looking for a comparative advantage over people like me, that's where you can get it, right? You're learning for the first, you've been at it for several years, but compared to me, you're just starting. You can decide where you want to focus your energies in learning the mathematics of writing sophisticated code. And for the next few years, it's all going to be about memory and memory complexity. So here's a particular model of memory for the NVIDIA. All of these graphics processors have something similar. There are threads, and there are many different threads which can be doing, these are like little processors, which can be doing information. The threads have their local memory, which is memory that they'll be changing the data for, right? That's where the data for the computation might be. Registers, which is data they're going to throw away, but they use counting, indices, things like that. There's shared memory, which can be shared among threads and synchronized if necessary. And then there's this other stuff that I was telling you about. There's global memory, which everybody can see. There's constant memory, which everybody can see but only read from it. And there's texture, which is this really powerful stuff where everybody can read and interpolate all in one go. So none of that is visible to you when you normally write code. And you have to, when we look at the syntax of CUDA coding, you have to declare what kind of memory you're using, and you have to think, why am I putting this in shared? Why am I putting this in global? Of course, you can ignore all that and just do the default, and you still, the good news is you still get about a 7-time speed up in our experience. So if you just took your code, whatever code you wrote or you've been given, and you tried to convert it over to run on the graphics processor, assuming you could do it, which is, I'm going to show you is not something to worry about, you should find 5 to 7 times speed up without knowing any of this memory management stuff. The real speed ups of 25 to 100 times come when you manage the memory. And that's very significant. So that's what I mean about the comparative advantages in people who know how to manage memory. Okay. Right. Well, okay, so the question is, surely someone else is going to do this. I mean, that's rephrased. And I think that's exactly right, but we don't know who. And it's going to be a few years. So you're sort of unlucky. This is the generation, those of us writing code today, we need to take advantage of the latest hardware because it's going fast and our competitors are going to do it. But there's not yet a dominant model for how to program these things. And so there's not a dominant language, and there's not a dominant optimization set of assumptions that everyone's going to use for their optimization. And I've been I'm a physicist, but I've been to some computer science meetings for the last 2 years. And the discussion there is how much of this to hide and how much to leave exposed. And I think we're still a few years from knowing who's going to win. And it could be, there's a product called Larrabee. Many people have heard of Larrabee? Okay, 2, 3, 4. Okay, so Larrabee is Intel's answer to this technology. Larrabee it depends on who you ask and which day you read the gossip blogs. It's either 64 or 128 CPUs on a chip, or 16. The idea is they're still CPUs, and so they still have scheduling and all that stuff built into them instead of very lightweight floating point units where you have to do more of the memory management yourself. So yes, it will happen. I don't know when, and I don't know which model is going to be right. So in the meantime, when did we have the meeting here? Was it 2 years ago or 1? 2 years ago. We had a meeting about using GPUs for Astro applications in particular, and we had the NVidia team come and present to us. And basically what they presented was embarrassingly useless to most of us in the room because they said, here's how you find the largest number in a string in parallel. And from that, you can construct all of the various operations that you need to do an astrophysical calculation. Well, we're not in the business, none of us typically are in the business of taking parallel primitives and building a whole code out of it. We want much higher level kinds of interfaces. It's gotten much better. I'll show you a little bit of it, but there's still some to come. This is why I think that say again? There's lots of good libraries. When I said that I moved to code over in a day, it's a bit of a swindle. What we did was we took a code that was dominantly spectral, pseudospectral, had lots and lots of FFTs in it, and FFTs are part of a library. So if you want to do a 1, 2, 3-dimensional FFT of any size, you can now, okay, here's where we are. If it's 2 to the n size arrays, you can call the library directly and life is good. Typically, we want something a little more. We might need factors of 3, or occasionally, you want a 17 in there for some stupid reason. There's not a library call for those kinds of things, or at least there wasn't yesterday. I don't know about tomorrow. But there are computer scientists who will make those available to you as a third party. So, and then, but your job then becomes, well, gosh, is the one that Rajesh gave me twice as fast as the one over here? And you don't want to be in the position of always checking to see which is the best library. I mean, it's okay to do it once every few months, but okay. There's another thing about Moore's Law that I wanted to go over with you, which is, okay, you can all see that. So the basic argument that we hear occasionally is let's just wait for the processor speed and we can substitute in that the GPUs. Let's say that we can all take advantage of GPUs effortlessly because somebody gives us a compiler that recognizes code we've written and puts it on the GPU for us. Can we wait for the processor speed to improve to solve complex problems without changing our algorithms? And the answer is basically, if your algorithm has linear asymptotic complexity, yes, you'll be well served. But most of us are doing problems where there's a different asymptotic complexity, n squared, n cubed, lots of other things where n is the number of mesh points or particles or whatever it is that you're thinking about in your calculation. So let's do the example. If you had 1 million variables and you had an n square algorithm and you wanted to wait on Moore's law to fix things, then you have to wait 16 generations, 2 to the 16th power, before the computer if you continue to use your order n square algorithm and just let the processor speed up and take full advantage of the GPU, and you don't change your algorithm, so I'm changing topics here, and you don't change your algorithm, it still takes 16 generations. And if Moore's law is 18 months for a generation, what is that, 24 years? If the GPU's twice as fast, that's still 12 years or something, to wait on the computer to solve your problems. So a critical question that we've been working on at Maryland is all of us use continually more sophisticated algorithms to get at problems that are deep. And so, there's a sort of, you have convolutions, and then you go to FFTs, and then there's, I forgot the name of it. There's order n methods, multi-block, that's not right. Multi-grid, thank you. Multi-grid methods, which are order n. And each one of those is more and more complicated to program, but for a sizable problem will work asymptotically much faster. And the critical question is, can you simultaneously imagine that you're going to improve your algorithms for the next 5 or 10 years and use more sophisticated algorithms with better algorithmic complexity, scaling, and use the latest hardware, which is getting very complicated to program because of all this exposed memory and all these hierarchies? And that's a critical question, because if you can't, there's no point in just switching over to the GPU, okay? You have to be able to continue to innovate in the things that you know and not just wait on the computer to do it. So this is a difficult and important question. And this is a couple of years old now. We showed this at that Astro GPU meeting. But in 1987, there was the FMM, or the fast multipole method, was laid out. It's a general method for accelerating dense matrix vector products. And basically, you can think of it, it's like the tree methods, or it reduces the computational and memory complexity from order n squared to n. And so you can, with great price and complexity of programming, reduce complicated problems down to order n algorithmic complexity. And the question that we asked was, can you program such a horribly complicated thing on a GPU without killing yourself? And so there's all sorts of tree transverses. This is just to give you an idea that there's regression, there's all data structures that are very complicated and dynamic. And so we had one guy working on this for 6 or 8 months, and he reports back that the data structure was extremely challenging to put into this new memory hierarchy. There was no simple mapping to the single processor multiple data architecture. So you can see these things yourselves. At the bottom, he says the low amount of fast local memory relative to the other kinds of memory was a real challenge. And the fact that there's no debuggers. 2 years ago, there was no emulation even of these graphics processors. So you launched, and if it didn't get the right answer, I don't know. So it was a really very challenging kind of world. Nevertheless, this guy was amazing, and he got things to working. P is the order of accuracy. Larger P is better. And basically, calculating both potentials and forces for 1 million particles, he was getting 72 times speed up over a Xeon. running on an Intel compiler with those kinds of compiler optimizations that are available to you. And to give you an idea, that's 1 million particles getting the forces between all of them in about a second a year or two ago. So that's good performance, and he was able to get correct answers. And basically this just, I'm not in this world, and so I know some of you are. In the in-body problem world, there's ways to define the effective performance, and this paper by Warren Salmon et al. Basically said, for a given size problem, this is how many flops it ought to take, and if you can do it in a certain time, that's an effective speed, even if you use a different algorithm with a different number of operations. Do you see what I'm saying? So what they found was the code was only running at 150 or 200 gigaflops on the graphics processor, but because the FMM was order n, when they had a large number of processors, they're getting a big benefit relative to this timing that assumed you using an order n square algorithm. And so they get a range of 25 to 50 teraflops effective. What does it mean? It means if you used the old algorithm, a simple order n square algorithm, and you used a processor that wasn't a GPU, you would have been at probably around 50 gigaflops, and here it's 50 teraflops. So there's factors of 1,000 lying around today. Okay. So you can do sophisticated algorithms on these things, but that was a work of desperation. That was a guy who basically locked himself in his office and didn't come out for a really long time. And that same guy then drove us into what's been now a 2.5-year project to develop a layer in between the old stock. You know, we all have either C or Fortran lying around, and then we'd like it to run on the graphics processor. Well, thinking of the Fortran versions right now, 90, 95, whatever, we said that we wanted to be able to maintain the code without too much pain, and it needed to be portable. We wanted to be able to move from one type of architecture to another, and we wanted to be able to take advantage of GPUs. So Nail and several students put together this flagon, which is a layer that sits between the NVidia product and Fortran code that you've already written. And it's available on SourceForge. It's linked on the website. This is the kind of way that your code ends up looking. And there's some other loops that aren't shown, but let me just show you this. This is the guts of a pseudospectral calculation of turbulence. And so in the original code, this was the subroutine that calculated the nonlinear terms. So you have some declarations of variables. You multiply by some kx and ky, do some Fourier transforms, do some more Fourier transforms, then do the convolution, kx times one times ky times the other minus kx times and ky the other way around. So you do a Poisson bracket, and then do a backwards FFT, scale by the appropriate factor, and that's the guts of a complicated fluid turbulence code of some kind. Okay, so this is a workhorse internal routine that's the standard Fortran version in our group. And this is what the Fortran looks like for the GPU. It's great. Instead of declaring variables complex, you declare variables of a type device variable, which we made up. You can call it anything you want. But the idea is that now this is part of uncovering the memory hierarchy. A device variable is something that lives in the global memory of the device. He's Russian, so all graphics processors are just device. So on the device is where the data lives. In the Fortran, these are all just pointers with meta information about sizes of arrays, leading dimensions, and so forth, so that we can do simple changes of size and so forth on the Fortran side. Then, instead of multiplying kx equals I kx times a, there's call device multiply. And what that does is it accomplishes the same element by element multiply of two arrays, one 2D array, one 1D array, element by element. It's called a Hadamard product. The kind of thing that you asked about before, such a simple thing is not available in the native instruction set of CUDA, which is the most advanced of these languages. So what am I saying? I'm saying if y equals ax And A is a vector, and Y and X are matrices, right? So there's lots and lots of, it's a nested loop. You have to break that out yourself. There wasn't any sort of implied anything. So you multiply these things, you do an FFT, and so forth. It all looks the same, and there's a couple of loops that get defined in CUDA, which is written in C, that you have to link to from this Fortran that actually execute those loops, but they're very, very simple. They're atomized at a low level, so you can, as I said, I was not an expert. I was able to write these loops in a few minutes just by seeing what other people had done. The difficulty of this, so this works great. I think the next slide is So this is just the slide that normally would go before the one I showed you. So this calculation of turbulence simulations, here's the size n, it's actually n by n, but we're just counting n, versus time, and so the CPU is great at small problems and stays basically in squared, because you understand what I'm saying here, it's a 2D array, but you just count the total number of points within. And so there's some, okay, so then the GPU is bad at small sizes, but then this is time, so the fact that its time is smaller at large problems means that it's performing very well, and the ratio of the two is about 25, so you get a 25 times speed up in that case. If you do a problem, in this case it was bigger than 128 by 128, which is not very small. So if you wanted to do a 512 by 512 2D turbulence simulation on your GPU, it's screamingly fast compared to your CPU. That's where the sweet spot is, okay? And those of you that have CUDA on your, or NVidia video cards, how many people here have them on your laptops? Right, about half. How many of you have loaded the software developer kit from CUDA? Okay, half of that. If you've done that and you're able to get it to run, you can see that they have codes like this already laid out for you in entirety, and you can use those as the building blocks for what you want to calculate. That's the kind of thing we'll do in the hands-on exercises, look at what's available and see how to construct more complex things. But it's great. You can actually, one of the things that is in the, that comes with the distribution is a program that has some fluid with tracers, and you drag your mouse across it, and there's turbulent eddies and whirls and everything, and it's all being calculated in real time. It's nice. Okay.
What is the reason that you need large problem sizes to achieve speed up? Is it the overhead of firing up these device functions?
Okay, so it's a good point. Thank you. There's a couple of things going on. First of all, the overhead was much, much worse until we learned some things. And in the conferences I've gone to, I think everybody's learned this by now. Let's say that you had a problem and there's some really computational intense nugget of the calculation, and you had in mind that you're going to keep the whole problem on the CPU, but just use the GPU to speed up that nugget. If that involves moving a sizable amount of data to the GPU, spinning for a while, and then moving it back, you'll be killed almost entirely by the moving of the data back and forth. And that, if you don't use these device variables and you're moving things back and forth all the time, you're limited to sort of 5 or 7 times speed up, even on large problems. So the overhead of movement was not in this. What we were able to do is leave everything on the processor. We do many time steps. I think I said 100 time steps. So you do many time steps on the GPU and then just report back an answer to check for accuracy. No, it is, I think it's that the parallel FFTs that, so they're doing FFTs that are distributed in some way. We tried to look under the hood and see what their FFT model was. And this is being taped, right? It'll be on the web, so I have to be careful. What we thought for some period of time was that they were actually using order n square algorithms but speeding them up with all these processors. Turns out we were wrong. As best we can tell, they're really doing real FFTs, but there is some overhead associated with doing things in parallel.
I wonder if it's just the vector. Do these have vector pipes in them?
They're not called, this is the NVidia, they're not called vector pipes.
Are there vector pipe lines?
Effectively, yeah.
Just get started for the
Yeah, that's probably, that's right, that's right. I mean, what you're doing is you're launching, typically with these things, the scale of the parallelization that you think about is launching hundreds of thousands of things at one time, rather than, in the vectorized world, we would think of 32 things going into a pipeline, and after the first 32 iterations were done, then the pipeline's full and we're getting 32 times speed up, and then there's a little bit of slowdown at the end when the stuff comes out of the pipeline. Here, you have the same kind of hidden latencies. Getting something from global memory is 600 clock cycles, so there's a substantial hit for going and bringing the data in, but there's so much, they manage millions and millions of threads really well so that they can hide almost all of that, but I guess that's the main latency we're seeing here. Okay, so our results were that we were doing these turbulence calculations on a pseudospectral kind of way. It's very data parallel, very easy to code, very easy to exploit the GPUs for that, but it's still nonlinear PDEs of interest. We can get 25 to 30 times speed up. This in-body force calculation required heroic effort to manage the memory. I can't read the code. A very customized algorithm, but it works, it gives a correct answer, and it's been verified, and it's pretty high performance, 1 million masses in a second calculating forces. For particle and cell, which I didn't talk about here, the improvements have been more difficult to achieve, and it's because of, again, memory. As particles move around, you can either access the particles in the same order, but then you need to be able to find spatial information in random, or you can do things the other way around. But in any case, something has to be found randomly. And when you read out of global memory, and it's not contiguous so that you can't pull it all up in a large stripe at once, you pay enormously. So we haven't gotten the huge speed ups in particle and cell. But if we do fake problems, which can be real, but they're not the general particle and cell algorithm, we can get 100 times speed up if we set up a problem where we can keep the particles coalesced in memory by some trick. But that's not a general solution.
So most of the performance gain essentially comes from very large data sets, large dense matrices. And so the memory streaming gives you the performance gain. Whereas if we have sparse matrices or vector scatter operations, then you will get the memory gain.
So there is some sparse linear algebra that's been built for the chip that isn't bad, but the last part of your statement, the general gather scatter, is slow, and the dense is great. So most of everything I would agree with you. In the middle, as I say, I've been to a couple of meetings the last couple of years. There's a lot of talks, people talking about how to do sparse linear algebra efficiently on these architectures, on different vendors, and those kinds of solutions are out there. It's not too bad. Okay. So I was one of the people that helped develop Flagon, and the thing that we figured out was that you needed this layer if you wanted to deal with Fortran. Many of you will have C codes or C++, which is much closer to the CUDA model and similarly to the other programming models. And you can move more quickly to take advantage of this stuff if you're in that world. Happy to work on those things with you. Let me see if there's anything else. So it's coffee time. The way because there's everyone here is interested in astrophysics, but as I said at the beginning, not everyone here is interested in parallel computing, and even fewer are going to be interested in detailed graphical processing kinds of things. So what we're going to do is, in half an hour, if you're interested, we can come back here and we'll sort of take stock of where the interest is relative to the already existing knowledge, and we'll figure out what we're going to do with the time that's scheduled. I have exercises and things, but maybe it's insulting or maybe it's too hard. I don't know. So let's go get our break.